Okay, picking up where we left off last time with the 5.6 Part 1 lesson on related rates. We just had to solve for dH/dt. We were virtually done. All we have to do is multiply through both sides by 500. And we'd see that dH/dt, the rate that the height is changing with respect to time, is, well, multiplying really by 5 times 100. 100 times 0.14 is 14. 14 times 5 then would be 70, and 70 times 2 would be 140. So that would be 140 feet per minute. And that is the rate, how fast the balloon is rising at that particular moment. Well, let's take a look at a second question. Second problem here, a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now, N-O-W, moving straight east. So here's what's happening. We've got, from the north, here's going east. We've got this cruiser, here's the police car, and I'll make this P for police. This police car, of course, is driving this way towards the intersection. We could even call this distance Y. We have the speeding car. We can call that point C for the car. We could call this X right here. The car is, of course, traveling due east. And just reading this through, it says when the cruiser is 0.6 miles north of the intersection. So again, this is where y would momentarily equal 0.6. It's only going to be 0.6 for the briefest of moments. The speeding car is 0.8 miles to the east of the intersection. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So there is a distance between the police and the speeding car. We could call that D if you'd like. And at that brief moment, when y is equal to 0.16 or 0.6 miles and x is equal to 0.8 miles, at that very brief moment, then the car is increased, the distance is increasing at 20 miles per hour. So we'd say dt, the rate at which that distance is changing with respect to time would be 20 miles per hour. Again, all of these parameters of the right triangle are changing. Nothing is fixed. X, Y, and the distance between them are ever changing. And it says if the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Well, I hope it's clear to everyone that we could use the Pythagorean theorem. We can say that d squared equals x squared plus y squared. And we can take derivatives. We'd get 2d. Take our derivative, we'd get dd dt. Take our derivative of x, we'd get 2x dx dt. Take our derivative of y squared, we'll get 2y dy dt. And very quickly, I think we can see that we are going to cross out the 2's. That's certainly something that we could do to make life a little bit simpler. And I think sometimes as we read this, we can see that, okay, so at this moment when the distance between the police car and the speeding car is increasing at 20 miles per hour, at that brief instant, that's when x is equal to 0.8, y is equal to 0.6. That's also when the police car is going 60 miles per hour. That's your rate of change for y. And I'm going to write that dy dt is equal to negative 60 miles per hour. This is so important for us to talk about. That length of y, as this police officer is driving towards the intersection, will decrease. It's going to shrink. And if you ever have a length that is getting smaller over time, it must have a negative rate of change with respect to time. That's how decreasing will show up. By way of comparison, you can see that the distance between the two cars was increasing. Just being told that, we would know that that would have to be a positive 20 miles per hour for d dt. We'd like to find out what dx dt is. Now, I think what happens very quickly is students will realize that they know what x is, they know what y is, they know what dd dt is, they'll know what dy dt is, and they'll know they need to find the speed of the car. The speed of the car, of course, is the speed of the speeding car. Find dx dt is really what we're asked to do. But very quickly, students will realize, either right now or as soon as they plug everything in, that there is something missing. We are missing the value of d, the distance between the two cars. And to find that, like we were saying in class, you really need to go ahead and plug in your value of x to be 0.8, plug in your value of y to be 0.6, and here then you can find your distance. We would find d via the Pythagorean theorem. In other words, we'd use the original equation to find that. And it's not hard to do. We can say d squared is equal to 0.6 squared, or 0.8 squared if you wanted to follow it exactly, plus 0.6 squared. Here's 0.64 plus 0.36. That adds up to 1. And then take a square root, you'd get d is equal to 1. So I'm going to plug in a 1 for my d. dd dt is a positive 20. My x is 0.8. I don't know what dx dt is. I'm going to find that. And my y, they told me, is 0.6. Dy dt, we know, is negative 60. Negative 60. So, wow, my goodness, working this out, we have 20 is equal to 0.8 dx dt. Multiplying 0.6, which is really 6 over 10, to negative 60, the 0 and the 10 would cancel out down below. Here you'd have negative 36. Add 36 to both sides, and you'd have 56 is equal to 0.8 dx dt. Solving for dx dt, you quickly will find that the speeding car is going 70 miles per hour. Okay, so we have one last problem left, and this is a classic problem, the inverted conical tank problem. It says water runs into a conical tank, and that's coming in at a rate of 9 feet per minute. So here's your tank, but what you definitely want to realize is there is water that is in fact coming in. And that water, of course, is going to be taking the shape of the tank that is containing it. Obviously, you can see that you'll have the water in the shape of a cone as well. But as the water is coming in, I hope you'd realize that this is volume. dV dt, the rate at which the volume of this water is changing, is positive 9 cubic feet per minute. If water is coming in, this volume is growing. It's getting bigger. So we would have a positive rate of change. The tank stands point down, like we've drawn, and it has a height of 10 feet. The tank also has a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Well, I hope it's clear that the water actually is in the shape of a cone also. We have this r for a radius, and we have h for a height, and that's the height of the conical water there. So I hope it's clear that we're going to have the volume of any cone, like we had in the beginning of our notes, would be 1/3 pi r squared times h. I know that in blue here is that volume of water, and I could take a derivative and very quickly find a dv dt. But on the right-hand side, r and h are both ever-changing. They're both functions of time. And I'd like to avoid the product rule if at all possible. How do we do that? Well, we do that through geometry. Look at this right triangle in red that I've drawn right here in the water. You have the radius of that circular surface of the water. You also have the height of the water, the depth of the water, you could say. And here is an angle in that right triangle. Now, of course, right now we could very quickly go ahead and draw in another right triangle. And I'd like to maybe make this stand out a little bit different. Let's maybe make it a thicker black right here. This big right triangle is going to be 5 feet for that side right next to the right angle. And then we've got 10 feet over here. But notice we'd be containing that same angle. This is what we call angle-angle in geometry. It means that we have similar triangles. Similar triangles mean that we can set up a proportion. R is to H just as 5 is to 10. And I'm going to reduce 5 over 10 to get 1/2. Now, we can solve for R or we could solve for H. But ultimately, the question that is being asked is how fast is the water level rising? So they want us to find dH dt, find how that height of the water is rising or changing, increasing, when the water is 6 feet deep, when h is equal to 6. In other words, I need to work with an h and find a dH dt. I would ultimately like to solve for r. I'd like to get rid of r because it's not helpful to me here. I'm interested in the height in dH dt. So multiply both sides by h. You'd have r is equal to h over 2. And very quickly, we're going to plug in my r of h all over 2. And then we're going to work this out. Squaring, I'll have h squared over 4 times h. It looks like 1/4 and 1/3 multiplied to 1/12. And h squared times h is h cubed. Taking derivatives with respect to time, we'd have dv dt. And we'd drop down a 3 here. Here's an h squared. And don't forget, we need a dH dt. Now our dv dt, we know, that's 9. And here we could even cross out a 3 and a 12 and to get a 4. We've got 1/4 pi. But I want my height to be a 6. So I'll have 6 squared here. And then we're going to look for dH dt. Now 6 squared, of course, is 36. And very quickly we'll see that dH dt over here can be solved for. 4 goes into 36 9 times. And I'll have 9 is equal to 9 pi dH dt. That means dH dt is 9 all over 9 pi. Another way to say it, dH dt is 1 over pi. And the units that we were using were feet. Time unit would be minute. So the water level is rising at about 1 over pi, or 1 over 3 feet per minute. So keep working at this. It just takes a lot of practice. We're spending 2 days just working off of this. We'll even have a third day where we get to review. But good luck to you.